Hey, welcome guys. Yeah, so after we're talking about this is my group theory lecture. So welcome to my group theory lecture. And previously I talked about direct product and direct sum and the inner direct product and exterior direct product, and we proved that they are actually the same, isomorphic. So we can use all this technique to prove the classification of the finite abelian group. Okay, so this is what I intended to prove, given the rigorous proof in this video. So this topic is very interesting, and I will use, let me just write down. So this is my first video about the classification of finite abelian group. Okay, so this is a famous theorem. So theorem says that all the finite abelian group, is a direct product. So you can use the inner or outer, but however they are the same, they're product of cyclics. Okay, so basically this G is just a Z modulo P K1Z or Z modulo P K2Z. Okay, so using these, you can easily, for example, let's using quickly say some example. Let's say you want to classify all the finite abelian group with order 4, then there's a obviously, right, the direct product of cyclic, so either Z2 or Z2 or Z4. And they are actually different because in the Z2 cross Z2, then every element is order 2, and Z4 you can find an element which is order 4, so they are different. Okay, and let's say you want to want to find abelian group with order 6, then it can at most be Z2 cross Z3 and also Z6, but they are isomorphic. So this is also I previously proved using the Chinese remainder theorem. So proof that the Zm cross Zn is isomorphic to Zmn if GCD of Mn are 1. Okay. So this is Chinese remainder theorem. So you can go to my previous 2 videos and see the proof. Okay, so in this video we are trying to prove this theorem. So there are many ways to prove it, right? So there are the one way is to using the module theory. And if you use the module theory, then you can use another powerful theorem says that all the finitely generated module over a principal ideal domain is the direct sum of cyclic module. So this is the module theory way to prove by application on abelian group, right? But I don't want to use this. So our idea is using the elementary and the plus some induction. Right, so this video will be very, very technical and very, very tricky because I want to step by step and proving this guy is true. This theorem is true. So the first step 1 is that notice that every group G, finite abelian group, is actually the direct product of its pseudo group. Let's say G is a P1 K1, P2 K2. Let's say Pn Kn, and they are different primes. Then G will be isomorphic to direct product of G1 tensor G direct product G2 up to, let's say, Gn, and each Gi is just Pi Ki. Okay, and this is our pseudo group. Because these are all the finite abelian, so each pseudo group must be normal, and by the pseudo theorem, when it's normal, it's unique, so you can easily, and they are coprime, right? So their product must be G. Okay, so now our theorem reduced to what? So our theorem reduced to, we only need to show that when G is a P group, let's say G is a P to N, and we want to show that in this finite abelian group case, so we are working on a P group, and the abelian is a direct product of cyclic, right? So there exists a A1, A2 up to AK such that this G is A1 product A2 up to AK, and then such that AI, let's say I write AI is a P to the, right? So it's subgroup, right? So let's say I play P to NI and I label the N1 greater or equal to N2 up to NK. Okay, and to satisfy, obviously they need to satisfy this. Okay, they need to satisfy the K need to be N, and also this A1 up to AK is not just some group with P group, right? Otherwise we didn't prove anything. What I'm trying to say is AI is just actually cyclic. So it's cyclic. So this guy isomorphic is Z P to the NIZ. Okay. So basically any P group P to N can always find the cyclic decomposition. Basically find the K number N1 greater or equal to N2 up to NK, their summation is N, and which each decomposition is cyclic. So once we prove this, then we prove that every abelian group is a direct sum of cyclic. Okay, and our proof using very elementary way. So this is why this proof looks so difficult, because this is elementary way. So we are not using a fancy idea. Okay, but still very powerful. Okay, so go through a proof. Really difficult, very tricky. Okay, so I want to show what? So I want to show that, let's say take G to be P to N. I want to show that each element X belongs to G should be written as what? Should be written as A1, alpha 1, A2, alpha 2, up to AK, alpha K. Okay, and the A1, let's say A1 is a cyclic group, right? So A1 has the Pn1 power, right? And its identity, so its order is Pn1 and A2 is Pn2. And then somehow this decomposition is unique. That by property of the inner direct product, then you can prove this G is actually the direct product of the cyclic. Okay, so let's try to find. So the idea is that how to find this first N1, right? How do you find this N1 such that this is the largest guy? Okay, so this is a simple, right? You just take that A1. So this is a step 1, right? So let A1 be the maximum order. The maximum A1 to be the element, A1 be the element with the maximum order. So maximum order of G. So which is A1 is the largest order such that it becomes identity. So now I can say since it's a P group, so order must be P to N1. So I define this as N1, right? So let's say A1 P to N1 is identity. Okay, then I can get A1 generated by small a1. Okay, so this is a cyclic group, which I already find the largest one. Okay, but I'm not saying this is true. I'm just go to definition. So the problem is that how to find N2. Okay, how do you find N2? So the very simple, right? So somebody give you this, then what you should think is quotient. So you can see there's a canonical quotient map from G quotient A1. So this guy is also a P group. Okay, so now I can define. I can say that I find the B2. Okay, so notice that this B2 belongs to G. It has maximum order in G modulo A1. So what I'm saying is that let's say B2 will map to B2 bar, where B2 bar is in G quotient A1, such that it has maximum power. Okay, so let's say this is P to N2. Okay, so that means that B2 bar, P to N2 will be identity in G quotient A1, but this translated into B2 P to the N2 must be what? Must be must belongs to A1, right? But my definition say that I choose N1 to be the largest prime, the largest order, right? So which prove that N2 should less or equal to N1. Okay, so trivial, right? Because if N2 is not greater than N1, then I should pick N2 in the first step, right? But now I pick N1, so N2 is dash equal to N1. Okay, but there's a problem, right? So let's say, so if I define A2 to be generated by B2, there is a problem, right? Because B2 intersection with A1 may be non-trivial. So there might be a case that A1 intersection with B2 may be non-trivial. So we need to adapt this B2, and in terms of we need to find something B2 related, right? And to make another generator. So this is the meat of this theorem. Okay. Okay, so let's see. Right, so from here we know that the P to N2 is the first power of B2 such that in A1. So let's see. So let's say this, suppose B2 P to N2 in A1. Okay, so let's say this is A1 to the I. Okay. And the node, so I can get A1 times I, let's say Pn1 minus N2. Right, so I just power Pn1 N2, right, become B2 P to N1. Okay, so P2 P to N1 must be identity. Why? Because P to N1 is the largest power, is the largest prime largest order of any group in any element in G. So if B2 P to N1 is not identity, then the first step I will not choose N1. Okay, so B2 P to N1 must be identity because N1 is the maximum order. Yeah, so it becomes identity. Okay, so but this means what? This means that A1 I P N1 minus N2 is identity, right? But A1 has A1 is the maximum order of P. So A1, the order of A1 is P to N1, right? So that means P to N1 divides I P N1 minus N2. So this condition tell me that P to N2 must divide I. So I can write I to equals to J. So J is some integer, P to N2. Okay. 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 So now I can define a new. So I define A2 to be B2 A1 minus J. Okay, and notice B2. So A2, right. So notice that if you do A2 to if you do the A2 of the P to N2, then you get B2 P to N2 and A1 minus P to N2 J, which this guy will be I, right, by definition. So combine A1 I with B2 B to the P to N2, then you will get identity. Okay, so this is the important identity. This important identity tell you that the order of the A2 at least the order of A2 should be P to N2, at most P to N2. Okay. Okay, so my claim is that as you define A1 intersection with the cyclic group generated by A2, it must be identity. Okay, the reason is follow, right? There's a suppose A2 to the power T will be in A1. Okay. So who should tell you that so by definition, right, your A2 is B2 A1 minus J. So it's A1 minus J B2 T will be A1. Okay. But this guy is in A1, right? So who should tell you that the B2 to the power T belongs to A1? Okay. But B2 has the power P to N2, right? As the order B2, so T will become P to N2. So P to N2 divides T, because the order of B2 is P to N2, right? So which tell you that your T is actually P to N2 times something, right? But the A2 to the P to the N2 as my construction is I already identity, right? So A2 to the T will be identity. So which proves that if A2 to the T become A1, then this guy must be identity. Proof. Okay, so we find A2, right? So I can define A2. So now you see this proof is so elegant that you can step by step do the deconstruction of finite abelian prime P group, and finally you get an answer. Okay, so but Okay, so now I already get A1 and A2, right? So what is the next step? Okay, the next step is keep going, right? So let me just do this one. So this one is the most the most intrinsic illustrate how the idea if you have two of them, right? So you can define your group G and divides A1 and A2, and you map there's an onto map. Then you can take N3, right? So I can take the element called B3, which map into B3 bar, has the maximum power, has a maximum order, P to the N3. Okay, so the first is that I claim the same, right? So N3 less or equal to N1 and N3 less or equal to N2. Right, definitely N3 less or equal to N2 and N3 less or equal to N1. Okay, and the reason is that, I know from my construction, right? B3 to the P to N3 must be in A1 times A2, right? But then B3 P to N3 must be in A1, and the B3 P to N3 must be in A2, right? So this shows that N3 less equal to N1 and N3 less equal to N2. Right? So this somewhat trivial because, right? Because you can choose this identity and improve this. You choose identity here and improve this. So very, very trivial. Okay, so now, so you might worry. So now we do the same thing, right? We need to ask this. So there's a possibility that this guy is still not identity. So let's suppose that B3 has some power. Let's say B3 got some strange power. Let's say P to N3, right? So B3 P to N3 must be A1 in A2, right? Because B3 bar has the maximum order P to N3 in G quotient A1 A2. So B3 to P to N3 must be A1 to some I1 and A2 to some I2, right? So this is true. Okay, but okay, so let's say we have this. Now I claim the same thing. I claim that the P to N3 divides I1 and P to N3 divides I2. Okay, the reason is that I can take, let's say, P to N. Let's say I take, so let's say B3 P to N2 must be in A1. Okay, so now okay, so this is the previous step, right? You just do adapt from the second reduction from the previous one. So you can take the let's say A1 I1 A2 I2 times the P N3 minus N2 minus N3, then this guy will be B3 P to the right, so P N3 times P N2 minus N3, so will be P3 B to N2, which is identity. Okay, so I'm sorry, not. So B3 P to N2 is in A1, right? Okay, so this tell you what? But these guys already in A1, right? So which tell you that A2 I2 P N2 minus N3 is in A1. Because this guy, the power in it, this guy already in A1. Okay, so this guy is in A1. But then what? But by previously, right? A1 and A2 you intersection is trivial, right? So remember A1 intersection A2 is only identity. So this guy already in A2, it must be identity, right? So right, that means Pn2 must divide this. Whew. Tricky. So what? So that means Pn3 must divide by I2. Okay, so we have this. Okay. Okay. So and the same reason. You can take B3 P to N1, right? And by previous, it must be identity. Otherwise, that in the first step, I will already choose. N1, right? So in this case, why this is true? Otherwise, then previously, if this is not A1, then previously I will not choose N2, right? So that means it's maximum power. This P to N2 is already the maximum order. Okay, so in this case, it's identity. So since it's identity, then I can say that I can do the exactly same thing, which is A1, I1, A2, I2, to the P to the N2 minus N3 is B3 P to N1, which is identity. Okay. Yeah. Follow this. This is B to the B3 to the P to N3. So this is N1, right? So this guy times this, the N3 cancel. This is identity. Okay, so from here you know that what? You know that this guy. Now you get this, right? Right. So you know what? You know that this A1, I1, Pn1 minus N3. So this guy is already in A2, right? This guy is also in A2. So this guy is also in A2, right? But A1, A2 also has the trivial, right? Has the trivial intersection. So same reason, the Pn1 will divide I1 times Pn1 minus N3. So Pn3 must divide I1. Okay, so my claim these two are true. Okay, so once these two are true, then we can do the same thing, right? So we can define, so I can define the I1 to be P to N3 J1 and I2 to be P to N3 J2. Okay. And I know that the B3 P to N3 will be A1 JP N3 A2 J2 J1 J2 Pn3. So I can define. So now you see the trick, right? So I can define A3. Now I can define A3 to be A1 minus J1 A2 minus J2 and times B3. Okay. Okay, so this is my definition of A3, and I can define A3 to be the generator of this smaller A3. Okay, and notice that this equation just tell you that A3 to the P to N3, you can do it, right? Become identity. Okay, just follow this. Okay, so the non-trivial part is to check. The non-trivial part is to check A1 intersection with A2 intersection with A3's identity. Okay, then once we do this, then we can do a reduction and show this process always keep going, and finally will exhaust all this group. Okay, so why? Okay, so this is I claim. Okay, so this is very simple. Let's say this is I already know that A1 intersection with A2 is trivial, right? So let's say A3 has some strange power T, which belongs A1 A2, right? So which tell you that the A3 is defined. Let's say A3. Remember that A3 is defined to be A1 minus J1 A2 minus J2 B3. So you get A1 minus J1 A2 minus J2 B3 to the power T belongs to A1 A2, right? But this is A1 A2, right? So which tell you that the B3 to the power T must be in A1 and A2. But what? But I know that the B3 P to N3 is the smallest power such that it become not smallest. The maximum power. This P3 B3 P to N3 is the maximum power of the element in a group such that the P to N3 will be A1 A2, right? But then so this tell you that the P to N3 divides T. Okay. Then what? Then by previously, I know that, okay, so let's say A3 P to N3 is E, right? So what? So A3 P to N3 is identity, right? So who tell you what? Who tell you that A3 P to a T must be identity, right? Because T divides P to N3, right? So if you get some A3T power which belongs to A1, A2, then this guy, this guy A3T must be identity. So you prove that their intersection are actually identity. Okay, so this is the second step, right? And then you can keep going. So the idea is that keep going. Then you can define a G quotient A1, A2, A3, and then take the largest power, keep going. And every time you take this, the group order will decrease, right? Always decrease at least by P. Okay, so finally, so after you do this, you can find A1, which is generated by a small a1, A2 generated by small a2, up to AK generated by small ak with order. So this is a constructive proof, P to N1, P to N2, up to P to Nk, such that N1 greater or equal to N2, greater or equal to N3, up to Nk, and satisfy the summation of Ni, I from 1 to K, will be our N. Let's say our G is P to N. So these numbers are called invariants. Are called invariant of the abelian group, finite abelian group. I should say the finite abelian P group. Okay, and the next video that we will prove that the two finite abelian P group are isomorphic if they have the exactly same invariants. So each abelian group, P group will give you a series of integers, let's say N1, N2, N3, up to Nk, and these integers are finite abelian P group. These integers are called invariants. So this integer can be different, right? So for example, yeah, so this is our theorem. So theorem is proof. Okay, so for example, let's consider the group with order 8, right? And then you have Z8, right? So Z8 has the this is 2 to the 3, right? So has the invariant 3. And then you can also consider, let's say, Z2 cross Z2 cross Z2. So it has the 1, 1, 1. And so you can consider Z2, Z4 cross Z2. So this is 2, 1, right? So you can see this corresponding to the so-called partition. So this is a partition of 3, okay? So actually, this is exactly the case for G equals to P to the N. Then the number of differences corresponding to partition. But in the next video, I will prove that this is actually the invariance. So in this video, we only prove that it's always right, can be written as direct sum of cyclic. Okay, so this is an elementary way to prove the classification of finite abelian group. Okay, so let me just write down our final theorem that we just proved, where if G is an abelian group with order P to the N, P is prime, then and the G, and then you can write G in terms of, let's say you can write G in terms of A1 cross A2 up to cross AK, where I should say at length, where each AI is a cyclic group with order P to Ni with N1 greater than equal to N2 greater than equal to N3 up to Nk greater than Nk greater than 0. And these N1, N2 up to Nk are called invariants. Yeah, this is the theorem that we prove. And then you just combine with the any finite abelian groups, the direct sum of is a CELO group, and each CELO group is a prime power group. Then you just put this theorem and combine everything, and you prove that every finite abelian group is a direct sum of cyclic. See you guys next video. Bye bye.